In the quiet, endless dark beyond the reach of any warm stellar wind, there is a machine still speaking to us. It was built by human hands in the late summer of 1977, assembled in clean rooms that smelled of metal and ambition, given a name that suggested exploration without end: Voyager. It left Earth carrying golden records etched with the sounds of whales and waves and a mother's first words to her child. And for nearly 5 decades, it has drifted outward, past the amber bands of Jupiter, past the shimmering rings of Saturn, and then further still, into a place that no human artifact had ever touched. In August of 2012, after 35 years of silent, patient flight, Voyager 1 crossed the Heliopause, the great turbulent boundary where the sun's magnetic influence finally surrenders to the vast, cold plasma that fills the space between stars, and it became the first object made by human beings to enter interstellar space. That moment was profound, historic, and widely celebrated. And yet it was never the end of the story. The cosmos does not offer neat conclusions. It offers thresholds, and beyond every threshold there is something new. What NASA has now confirmed, from data gathered across more than a decade of interstellar flight, is that Voyager 1 has crossed into something stranger and more revealing than anyone had predicted. Not simply interstellar space, that label, it turns out, was too broad, too simple, but a distinct, structured region within the interstellar medium itself, a place where the density of the plasma rises in a steady, almost architectural gradient, where faint but persistent electromagnetic waves ripple through the near vacuum, like the last reverberations of some ancient cosmic event, and where the magnetic field lines, still anchored in a direction that puzzles heliophysicists to this day, suggest that the boundary between what is ours and what is not ours is far more complex, far more layered, than the models of the late 20th century ever imagined. The confirmation is not a single dramatic announcement. It is a slow, cumulative recognition that has emerged from years of meticulous analysis, and it forces us to reconsider what we mean when we say that we have left the solar system. To understand what Voyager 1 has found, it is necessary to travel backward in thought, not in space, and to sit for a moment with the structure of the heliosphere itself, that immense protective bubble that the sun blows into the surrounding galaxy by the sheer force of its solar wind, a constant outward stream of charged particles, mostly protons and electrons, racing away from the corona at supersonic speeds. The heliosphere is not a rigid shell. It is a dynamic, breathing entity, shaped and reshaped by the pressure of the interstellar medium pushing back against it, compressed on one side and elongated on the other, more like a comet's tail than a sphere, despite its name. For decades, scientists understood the heliosphere as having a few key zones: the termination shock, where the solar wind first slows from supersonic to subsonic speeds as it begins to feel the resistance of the interstellar medium; the heliosheath, a thick, turbulent outer layer, where the solar wind piles up, compresses, and heats to millions of degrees; and finally, the heliopause itself, the sharp contact boundary where the sun's influence ends and the interstellar medium begins. Voyager 1 crossed the termination shock in December 2004, at a distance of about 94 astronomical units from the sun, and then spent nearly 8 years traversing the heliosheath before reaching the heliopause in August 2012. During that long crossing, the spacecraft reported that the outward speed of the solar wind had dropped to 0, that the intensity of the magnetic field was climbing, and that the environment had grown increasingly turbulent, as if the probe were pushing through the outermost layers of a cosmic atmosphere that refused to let go gracefully. When Voyager 1 finally breached the heliopause, the change was unmistakable in the data. The density of the surrounding plasma, measured indirectly by the spacecraft's plasma wave instrument, since the primary plasma spectrometer had failed long before, back in 1980, just after the Saturn encounter jumped by a factor of at least 20, perhaps as much as 50, exactly as pressure balance models of the heliospheric boundary had predicted. The first reliable electron density measurement in the interstellar medium, recorded on the 23rd of October 2013, at a distance of 122.6 astronomical units, yielded a value of approximately 0.055 particles per cubic centimeter, an almost inconceivably thin gas by terrestrial standards, a vacuum far better than anything produced in laboratories on Earth, and yet substantially denser than the plasma inside the heliosheath. The temperature of the interstellar plasma, meanwhile, registered at around 30,000 to 50,000 Kelvin, hot but extraordinarily tenuous, a heat that would not burn a spacecraft because there are simply not enough particles to transfer meaningful thermal energy to its skin. Voyager 1 had entered the very local interstellar medium, the VLISM, a zone shaped by the interaction between the Sun's extended influence and the ambient conditions of the Milky Way's Orion Arm, and for a time, it seemed that the spacecraft had finally arrived at the unchanging, uniform void that science fiction had always imagined lay beyond the solar system. But the void was not uniform. It was not unchanging. And that is where the new confirmation begins. In the years following the Heliopause crossing, Voyager 1's plasma wave instrument continued to detect occasional bursts of radio emission faint oscillations in the electric field at the local plasma frequency, triggered when shock waves from the Sun, traveling outward through the heliosphere, slammed into the denser interstellar plasma just beyond the boundary. These events, known as plasma oscillation events, gave scientists brief, precious snapshots of the local electron density, and each snapshot revealed a slow but unmistakable trend. The density was rising as Voyager 1 moved further from the Sunday. By 2020, after the spacecraft had traveled nearly 30 additional astronomical units into the interstellar medium, the density had climbed from that initial 0.055 per cubic centimeter to more than 0.12 per cubic centimeter, more than doubling in less than a decade. This was not the behavior of a uniform medium. It was the signature of a density gradient, a structured transition zone extending far beyond the classical heliopause, a region that no model had fully anticipated. Then, in 2021, a team led by Stella Koch-Ocker and colleagues at Cornell University, working with data from the Voyager 1 plasma wave system, published a discovery that fundamentally altered the picture. They had found, buried in the faint background noise of the interstellar plasma, a persistent, continuous, very weak emission, not the sporadic bursts triggered by solar shocks, but a steady, ever-present signal that could be used to measure the plasma density continuously, rather than in isolated snapshots. The signal was extraordinarily subtle, a plasma line emission generated by the natural thermal motion of electrons in the interstellar medium, and it required years of careful analysis to separate from the instrument's own noise floor. But once it had been identified and verified, it became a kind of steady heartbeat from the interstellar medium itself, a continuous measurement tool that no one had expected Voyager 1 to possess. And what that steady signal revealed was that the density gradient extended further still, that the spacecraft was moving through a structured, evolving plasma environment that showed no sign of leveling off, no indication of reaching a final, uniform interstellar baseline, even as it passed beyond 150 astronomical units from the Sunday. This is the core of what NASA has now confirmed. Voyager 1 has not simply crossed into interstellar space and left the Sun behind. It has crossed into a complex, dynamic, structured region within the interstellar medium, a region that may represent a previously unrecognized transition layer, a forehearth of the true interstellar medium, shaped by the accumulated influence of the Heliosphere over millions of years of interaction with the surrounding galactic environment. The data suggests that the Sun's reach does not end abruptly at the heliopause, but extends its influence into the interstellar medium through charge exchange collisions between fast, neutral atoms born in the heliosheath and the ambient interstellar plasma, creating a broad, diffuse boundary that may span 100 astronomical units or more before the medium finally relaxes to its undisturbed galactic state. Voyager 1 is inside that boundary now, measuring it from the inside. And what it is finding is that the boundary between a star and the galaxy is not a wall. It is a landscape, a terrain, a place with its own structure and history and physics, far richer and stranger than the simple concept of outside could ever capture. And yet, even as the plasma density data tell a story of a structured, graded transition into the galaxy, a story that grows richer with every astronomical unit, Voyager 1 puts between itself and the home star there is another set of measurements, equally venerable and equally perplexing, that has refused to conform to expectations since the very moment of the Heliopause crossing. The magnetometer aboard Voyager 1, an instrument that has been measuring the strength and direction of the ambient magnetic field continuously since long before the spacecraft reached Jupiter, has delivered one of the most persistent scientific puzzles of the entire mission. The magnetic field direction did not change at the Heliopause. For decades, the standard theoretical picture of the heliospheric boundary had assumed, indeed, had required that the magnetic field lines carried by the solar wind would be fundamentally different in orientation from those of the interstellar medium, and that crossing the Heliopause would therefore produce a distinct rotation in the field direction, a clear magnetic signature of departure from the Sun's domain. But when Voyager 1 crossed that threshold in August 2012, the magnetometer saw only a smooth intensification of the field strength, a compression consistent with the pileup of magnetic flux at the boundary, while the field direction remained stubbornly, inexplicably aligned with what it had been inside the heliosheath. The field was stronger, yes, roughly twice as intense, but it was pointing in the same direction. It was as if the spacecraft had passed through a door into a new room and found exactly the same wallpaper on every wall. This was not a failure of the instrument. The Voyager magnetometer, built under the leadership of Norman Ness at the University of Delaware, is one of the most robust and carefully calibrated devices ever sent into deep space. And its readings have been verified across decades and across both Voyager spacecraft. Nor was it a failure of the basic physics of the heliopause crossing the particle data, the plasma wave data, the cosmic ray data all agreed that Voyager 1 had left the heliosphere. The magnetic field direction puzzle was, instead, a failure of imagination, a reminder that the boundary between a star and the galaxy is not a simple geometric surface across which every physical quantity changes simultaneously, but a complex, three-dimensional, time-dependent structure in which different physical processes decouple from one another, each crossing its own threshold at its own distance in its own way. The magnetic field, it now appears, may connect across the heliopause through a process of magnetic reconnection, the same explosive reconfiguration of field lines that powers solar flares, stitching the Sun's magnetic influence into the interstellar field in a tangled, gradual braid, rather than a clean break. Alternatively, the interstellar magnetic field in our local region of the Orion Arm may simply happen to be oriented in roughly the same direction as the heliospheric field at the point where Voyager 1 crossed, a coincidence of geometry that has profound implications for how the heliosphere interacts with its surroundings, since the orientation of the interstellar field is one of the primary factors determining the shape, size, and permeability of the entire heliospheric bubble. While Voyager 1 has been probing these mysteries alone in the northern hemisphere of the heliosphere, its twin, Voyager 2, has been traveling a different path entirely. Launched 16 days before Voyager 1, in August of 1977, but on a slower trajectory that would take it past not only Jupiter and Saturn, but also Uranus and Neptune, the only spacecraft ever to visit those ice giants. Voyager 2 has been moving southward relative to the plane of the solar system, tracing a complementary arc through the outer heliosphere, and, since November of 2018, through the interstellar medium itself, Voyager 2's crossing of the Heliopause, at a distance of approximately 119 astronomical units, provided the first comparative dataset in human history. Two spacecraft, built to the same design, carrying similar instrument suites, crossing the same cosmic boundary at two different locations, at two different times, along two different trajectories. The differences between the two crossings were as illuminating as the similarities. Where Voyager 1 had found a relatively thin, clean heliopause, the transition from heliosheath plasma to interstellar plasma occurred over a distance of less than half an astronomical unit. Voyager 2 found a thicker, more complex boundary layer, with multiple crossings and recrossings of the plasma density threshold, as if the boundary were rippling, undulating, breathing in slow motion under the pressure of a variable solar wind. Voyager 2 also carried a functioning plasma spectrometer, an instrument that had failed on Voyager 1 decades earlier, and so it was able to measure the interstellar plasma directly its temperature, its velocity, its composition, rather than relying on the indirect radio wave method. And what Voyager 2 confirmed in its own independent data was that the interstellar medium was not only denser than the heliosheath plasma, but also hotter, slower moving, and rich in the signatures of a galaxy that has been processing stellar material for billions of years. Together, the two Voyagers have now mapped the heliospheric boundary at two distinct locations separated by more than 100 astronomical units, and the combined picture they paint is of a boundary that is fundamentally asymmetric, more compressed on the southern side, more extended on the northern side, consistent with the idea that the heliosphere is not a static bubble, but a bow-shaped structure plowing through the interstellar medium at a speed of approximately 23 kilometers per second, driven by the sun's motion through the galaxy. But the Voyagers have also revealed that the boundary is not just asymmetric in shape, it is asymmetric in time. The heliopause moves, it breathes, it expands and contracts in response to the 11-year solar cycle, swelling outward during solar maximum when the solar wind pressure increases, and contracting inward during solar minimum when the wind slackens. And superimposed on this solar cycle rhythm is a longer, slower modulation driven by the sun's passage through regions of the interstellar medium that are themselves patchy, inhomogeneous, shaped by ancient supernova shock waves, and the slow churn of galactic rotation. The heliosphere, it turns out, is not a fortress wall. It is a shoreline, constantly reshaped by the tides of the galaxy. And it is here, at the intersection of the Voyager data and the broader astrophysical context, that the new confirmation takes on its most profound dimension. The structured transition region that Voyager 1 is now traversing, this forehearth of the interstellar medium, with its rising plasma density and its persistent electromagnetic whispers, is not unique to our Sunday. Every star in the galaxy that possesses a wind creates its own astrosphere, its own bubble of influence carved out of the interstellar medium. And every such astrosphere must have its own complex, multi-layered boundary region shaped by the same physics that Voyager 1 is now encountering. The Sun's heliosphere is therefore not merely our local cosmic environment. It is a laboratory, a natural experiment in plasma physics and magnetohydrodynamics that we can study in situ, with instruments that we place there with our own hands, and the lessons we learn from it will apply to every star in the sky. When astronomers observe the astrospheres of other stars, the bow shocks of Betelgeuse, the wind-blown bubbles around hot O-type stars, the magnetospheres of exoplanets orbiting red dwarfs they are seeing, from a distance of light years, the same physical processes that Voyager 1 is now measuring from the inside, particle by particle, wave by wave. And yet, for all the grandeur of this scientific vision, there is a quiet, inescapable poignancy to the Voyager mission at this late stage of its life. The spacecraft is dying slowly, gracefully, with the dignity of a thing that has far outlived its design specifications, but dying nonetheless. Voyager 1 launched with 10 scientific instruments, As of 2025, only 4 remain operational. And each year, the mission team at the Jet Propulsion Laboratory must make difficult, irreversible decisions about which instruments to sacrifice to preserve enough electrical power for the others. The spacecraft's 3 radioisotope thermoelectric generators, which convert the heat from decaying plutonium-238 into electricity, lose about 4 watts of power every year. The total available electrical power has now dropped below the threshold, at which all instruments and all heaters and all subsystems can be maintained simultaneously. And so, the engineers and scientists who have devoted their careers to this mission, some of whom were not yet born when Voyager 1 launched, must choose, deliberately and painfully, what to turn off and what to keep alive. In February of 2025, the cosmic ray subsystem was shut down, silencing an instrument that had been measuring high-energy particles from the galaxy for nearly half a century. In April of 2026, the low-energy charged particle experiment followed, ending a data stream that had traced the solar wind from Earth to the edge of the Heliosphere and beyond. Each shutdown is a small death, a narrowing of the spacecraft's senses, a step toward the final silence that awaits sometime in the early 2030s, when the last instrument will be switched off, and Voyager 1 will become a mute, blind ambassador, still traveling but no longer reporting, still moving outward at 17 kilometers per second but no longer telling us what it finds. There is something deeply human in this slow farewell. Voyager 1 was never designed to last this long. Its primary mission was supposed to end after the Saturn encounter in 1980, a mere 3 years after launch. Every day since then, more than 16,000 days has been borrowed time, a gift from the ingenuity of engineers who have figured out how to nurse a 49-year-old computer with 69 kilobytes of memory through crises that would have ended a lesser mission a dozen times over. Stuck thrusters, failed gyroscopes, a broken data system that in 2023 began transmitting gibberish and required a remote software patch sent across 22.5 hours of signal travel time to a computer whose architecture predates the personal computer. Révolution. The fact that Voyager 1 is still transmitting at all, at a distance of more than 24 billion kilometers, with a signal strength measured in attawatts billionths of a billionth of a watt, is itself a kind of miracle, a triumph of persistence and care that will almost certainly never be repeated in quite the same way, because no future mission will combine the specific historical circumstances, the rare planetary alignment that made the Grand Tour possible, and the sheer audacity of sending a machine into the void with the expectation that it would keep speaking for half a century. There is a particular kind of silence that surrounds a spacecraft at the edge of everything, not the silence of empty space, which is never truly silent when you listen with instruments sensitive enough to catch the plasma waves and the cosmic rays and the faint radio hiss of the galaxy. But the silence of distance itself, the silence of knowing that every word sent from Earth takes nearly an entire day to arrive, and every reply takes another day to come back, so that the conversation between the spacecraft and its makers is not really a conversation at all, but a kind of slow, ritual exchange, a call and response stretched across the void at the speed of light, which in the face of 24 billion kilometers begins to feel not like speed at all, but like a gentle, patient drifting of signals through the dark. Even now, as NASA confirms what the data have been whispering for years, that Voyager 1 has crossed into something new, something structured and unexpected within the interstellar medium, the spacecraft itself knows nothing of the confirmation. It simply continues to measure, to encode, to transmit, following a program written decades ago by engineers who are now old or gone, trusting that someone, somewhere, is still listening. And what Voyager 1 is measuring now, as it pushes deeper into this extended transition zone, is beginning to align with theoretical predictions that were once considered speculative, even radical. The idea that the heliopause is not a single sharp surface, but the innermost edge of a broad, Diffuse interaction region, sometimes called the outer heliosheath or the heliospheric boundary layer, has been circulating in the plasma physics community since the early 2000s. Advanced by researchers like Gary Zank, Nikolai Pogorelov, and Mera Vofer. Their magnetohydrodynamic simulations run on supercomputers that model the entire heliosphere as a three-dimensional, time-dependent plasma flowing through a magnetized interstellar medium have consistently shown that charge exchange collisions between energetic neutral atoms born in the inner heliosheath and the ambient interstellar ions can transfer momentum, energy, and mass across the classical heliopause, creating a broad hydrogen wall and a complex multi-structured boundary that extends tens to hundreds of astronomical units into the interstellar medium before the plasma finally settles into an undisturbed state. The Voyager 1 density data, the steady, gradient-like rise from 0.055 to more than 0.15 particles per cubic centimeter over a span of some 40 astronomical units, now matches these simulations with a fidelity that is genuinely surprising, suggesting that the models have captured essential physics that the simpler, older picture of the heliosphere simply missed. And yet, even as theory and observation converge, new questions emerge. The persistent plasma waves detected by Voyager 1, the continuous, weak emission at the plasma frequency that Acker and her colleagues identified in 2021, have now been observed to fluctuate on timescales that suggest the interstellar medium, even at these vast distances, is not quiescent. It is stirred by compressive turbulence, perhaps driven by the remnants of ancient supernova shockwaves that passed through this region of the Orion Arm millions of years ago and have not yet fully dissipated. The turbulence, in turn, may be energizing particles, accelerating cosmic rays through a process known as diffusive shock acceleration, and contributing to the complex, non-thermal spectrum of radiation that pervades the interstellar medium. Voyager 1, with its aging but still functional cosmic ray detector and its plasma wave instrument, is now sampling this turbulence, directly measuring the eddies and fluctuations in the interstellar plasma at scales from kilometers to astronomical units, building the first in situ picture of how turbulence behaves in the medium between the stars. These measurements are unique. No other spacecraft has ever reached this environment, and no other spacecraft will for at least another generation, if ever. The data Voyager 1 returns in these final years of its operational life will likely shape our understanding of interstellar turbulence, cosmic ray propagation, and stellar wind interactions for decades after the spacecraft itself falls silent. And falls silent, it will not in failure, but in completion. The engineers at JPL estimate that, sometime around 2030, the available electrical power will drop below the minimum needed to operate even a single scientific instrument. The radio transmitter will still function for a few years beyond that point, sending a carrier wave a pure, unmodulated tone as a beacon, a proof of continued existence before the power drops further, and even that faint tone fades below the noise floor of the deep space network's most sensitive receivers. After that, Voyager 1 will continue its journey in perfect, irreversible silence, a ghost ship carrying the golden record through the interstellar dark, its trajectory bent only by the gravity of the galaxy itself, its speed 17 kilometers per second, or roughly 1 astronomical unit every 3 months unchanged by the frictionless vacuum, carrying it ever outward toward the constellation Ophiuchus, where in approximately 38,000 years it will pass within 1.6 light-years of a star called Gliese 445, a red dwarf that is itself moving toward the Sun, so that by the time Voyager 1 arrives in its neighborhood, Gliese 445 will be one of the closest stars to Earth. That encounter a silent, unpowered flyby of a machine built in the 20th century past. A star that no human being will ever see with the naked eye is the closest thing to a destination that Voyager 1 will ever have. But to speak of Voyager, 1-inch terms of destinations is, in a sense, to miss the point. The spacecraft's purpose was never to arrive. It was to depart, to cross, to leave behind, to push outward beyond every known boundary and report back on what it found there. And what it has found, in this final and most profound phase of its mission, is that the boundaries we draw around our cosmic home are not walls at all, but veils layered, permeable, dynamic structures that connect the solar system to the galaxy in ways that are intricate, intimate, and still only partially understood. The Sun is not an isolated star. It is a participant in a vast, continuous galactic ecosystem, exchanging matter and energy and magnetic flux with its surroundings across a boundary that is not a line but a region, not a surface but a volume, not an ending but a transition. Voyager 1 has crossed into that transition, is inside it now, measuring it, and the measurements are telling us that the space between stars is far from the uniform vacuum of classical imagination. It is a textured, structured, living medium shaped by the accumulated history of every star that has lived and died in this arm of the galaxy over the past several billion years. And so, when NASA confirms that Voyager 1 has crossed into something new, the confirmation carries a weight that goes beyond the scientific. It is a confirmation that the cosmos, even at its most fundamental level, the level of plasma density and magnetic field direction and electron oscillation frequency, is richer and stranger and more intricately organized than the human mind, in any given generation, has been able to imagine every time we have drawn a line in space and said, here the sun ends and the galaxy begins. The universe has shown us that the line is an approximation, a simplification, a story we told ourselves to make the vastness manageable. And then it has invited us to draw a more nuanced line, a more careful line, one that acknowledges the gradients and the turbulence and the slow, complex mingling of influences across distances so immense that the spacecraft measuring them was launched before most of the scientists analyzing the data were born. This is not failure. This is the rhythm of discovery itself, the successive refinement of our mental maps, each generation passing a slightly more faithful picture to the next, each Voyager data point a small correction to a grand, evolving portrait of our place in the galaxy. In the end, perhaps the most moving thing about the Voyager mission is not the distance it has traveled or the discoveries it has made, but the simple, stubborn fact that it is still out there, still transmitting, still extending the reach of human awareness into a realm that, without it, would remain entirely abstract, a domain of equations and simulations and telescopic inference, rather than a place that a machine we built has touched and tasted and reported on. Every day that Voyager 1 continues to operate is a day that the interstellar medium is not merely a concept, but an environment, a real physical location where a human artifact is present, measuring, witnessing, enduring. The spacecraft has become something more than a scientific instrument. It has become the farthest outpost of a species that, for all its flaws and divisions, has managed, occasionally and magnificently, to reach beyond itself, to send a piece of its curiosity into the dark, and to keep listening across billions of kilometers and nearly 50 years for the faint, precious signal that says, I am still here. The boundary has been crossed. There is more to discover. And the story is not over yet.